All right. So hi, everyone. Welcome to the South Bay Systems Meetup. This is by far the largest meetup we've ever had. And thank you, everyone, for joining. Thank you. And today we actually have over 600 signups. So we'll post the stream. We'll post the recording online after this talk. And who are we? So we are South Bay Systems organizers. We are nonprofit. We are independent, community run. We organize tech talks and coffee chats roughly once a month, and we're not affiliated with any company, but we do take sponsorships. So if you're interested in hosting a talk like this at your office, please let us know. And then we welcome any talks on systems programming, and if you have any engineering challenges, any great solutions, any hacks you want to present, please let us know as well. And a fun fact, how do we get started? We have to thank Andy for it. So a few organizers, me, Alex, and Ingjun actually met at the SF Systems Meetup back in November 2024 at Andy's talk. And then the three of us decided that it was a long drive from South Bay, so we should start something for the South Bay people as well. So that's how we get started. And thanks, Andy, for bringing us together. Do you remember at the Amplify office last year? You gave a talk about what goes around, comes around, around, and around. Excel, yes. Okay, sorry for me. Okay. October 2024 at Excel office in San Francisco. Anyways, thanks, Andy, for inspiring us to actually start a talk series in South Bay. And today, we're really appreciate Databricks for sponsoring this event. And really thanks, Osama, for organizing everything.
Hello, folks. Thanks for coming out. So Databricks is a place where you can do a lot of systems programming. And we have a couple announcements for you guys. First off, new grad applications, they are roaring and they're going to drop tomorrow. So if you are an intern or looking for a new grad position or know someone who's looking for a new grad position, please implore them to apply. Moreover, we have offices all around the world. We continue to grow and grow. So you can check out our America, Europe, and Asia offices right there. And of course, we have a QR code just for you guys to sign up for this event in case you're curious about like recruiting opportunities at Databricks. I'll give you guys a moment. Feel free to take out your phones, check out this QR code, or talk to me, Susie over there, or some of the other recruiters that we have today if you're interested in a position. There's a lot of cool stuff going on at Databricks. Now I'll hand it off to Ipo to introduce Andy.
All right. Thank you so much. Hello, everybody. My name is Ipo. I'm an engineer. I recently joined Databricks as well. I'm going to go back to how do you go to the previous slide? You can take a little more time. Like me, you can join. I can tell you that the feeling here, the momentum is amazing here, and it just feels like when I joined AWS 10 years ago, and I hope we have a very good run for the next decade or more here as well. All right, let's talk now about Andy. So Andy and me, we're doing our PhDs in parallel. So I kind of know Andy since he was a super annoying first-year grad PhD student. We were working on data on deterministic transaction execution back then. Fuck you. As usual. So yeah, it's an incredible teacher and database systems researcher. The database systems class he's teaching is the best in the world. Whenever I talk to some junior engineer or graduating student, I'm telling him to go and follow Andy's classes because it's incredible. And I'm very excited of what he's going to tell us today. I'm also very happy that he's healthy. Yeah, he was under the radar for a while because he was going through some, and now I'm super happy to see Andy here and looking forward to his talk. All right, without any further, Andy, take it over.
Share screen. Yep. I did that. This?
Yes.
Okay, make sure it works. All right. What?
Oh, you have
Yeah, that should work, hopefully. All right, can you guys hear me in the back? Okay, awesome. I'm gonna take a photo because every time I come here, the crowd gets bigger. And they put me in better offices or at better rooms. So thanks for everyone coming out on a Wednesday. So today's talk is gonna be sort of a survey on what the sort of state of the art looks like in the world of automated database tuning. And obviously we're gonna talk about LLMs, we'll get there in a second. But this is the topic that I've been working on actually since I started at Carnegie Mellon over 10 years ago in 2013. And as we see as we go along, we'll sort of cover what the sort of history of automated database tuning looks like. And we'll see when we talk about the newer things, how quickly the field is accelerating. And obviously because of all the interest and energy being put behind AI and LLMs. So there we go. So for this audience, I shouldn't have to explain why databases are hard or why tuning databases are hard. But I want to sort of cover the 4 key areas where you want to use automation or to optimize these systems to make them work better, store data more efficiently, and hopefully cost less money. So the first thing you can modify or tune in a database system are the system knobs. So think of these are like the runtime parameters every database system exposes to you to allow you to control the behavior of the system, like how much memory to allocate for your buffer pool, caching policies, when to flush out the log disk and things like that. And the reason why these knobs exist is because when the database system developer was building the system, like the actual person writing the code, at some point they had to make a decision of like how much memory to allocate for this hash table. And then, but rather than trying to do something adaptive or be clever, they just expose it as a knob. So they assume somebody else is going to come along and know how to tune it for the workload of the application, right? And obviously, before you know it, you have hundreds of knobs, and they have a bunch of dependencies, and it's not non-trivial to figure these things out. So the next thing you can tune are what we'll call sort of physical design. So this is like one of the original problems that people thought about when relational databases were first invented in the 1970s. But the idea that you're going to have this logical abstraction layer of the relational model in SQL, but then somebody else needs to come along and figure out what the data structure should look like to actually store your data. So this is like picking what indexes you have, picking what index types you should use, how to partition your tables, how to do materialized views, or what materialized views you could even want, right? And this is really hard to do because just picking what indexes you need to have is an NP hard problem. So now you compound that with all the other choices you have, it becomes very difficult. All right, so the next one is query tuning or query options. So these are parameters or flags you could set that control what physical plan the data system is going to use to execute your query. So these are sometimes called plan hints, right? Telling it like what join order should use, what index you should use for a query and so forth. In some cases, you also can do query rewriting. Oh, hold up, that is alarm in the East Coast for bath time, sorry. For my 5-year-old. A query rewriting would be like taking the original SQL query, throwing it through some kind of tool that then rewrites it into a form that the database system's query optimizer is better able to handle. Postgres, for much of you love it, is a terrible query optimizer. It chokes on nested queries. So if you can rewrite things as CTEs or joins, it's going to be in better shape or better position to kind of try to come up with a better query plan that's more efficient. And the last one I'll call sort of loosely categorized as what I'll call lifecycle management. And these are things you would do if you're maintaining or operating a database system over long periods of time, right? Like deciding when you want to scale up or scale out, deciding whether you want to upgrade the software version, like Postgres puts out a new version of major version of Postgres every year. So should I upgrade? Yes or no? Should I upgrade my hardware? Yes or no? When I want to do migrations, maybe going from staging to production, right? These are the things most people don't think about, but are really, really hard to do if you're trying to maintain a data system over long periods of time with an application that's being actively developed. So it goes without saying, and of course you're all here because of the title, like this is a very, very hard problem to do for one database system, But now if you think about if you have a fleet of these systems, there's no way any one human or a team of humans could make all these decisions for every single application or every single database instance. So this is a clear case where automation is a good idea, and people have been trying to do this for a long, long time. So as I said, I want to go through the sort of the past, present, then the frontier and the future of what database automation looks like. And I was trying to think of what imagery I could use to show these different stages over this big timeline. So let's say that we want to go back all the way from the beginning of when people first started thinking about this problem in 1975 to the modern era. So I was trying to think of what person or what thing could I show that has been around this long and has evolved and changed over time so we can see how things change with that person. And so the first thing I thought about doing was going with, actually, sorry. If you only care about LLMs and you don't want to pay attention, you can tune out the first half. We'll jump to LLMs here. Sorry. All right, so I was thinking, what person could I use to decide for this first era, who's evolved over the time? And so my first choice, I was going to use Tom Cruise, right? Because Tom Cruise has been in a lot of movies, right? He has sort of aged gracefully over the years. And so I'm like, all right, great, I'll use pictures of Tom Cruise. But then I forgot that Tom Cruise's daughter now goes to Carnegie Mellon. And let's just say, without calling me out directly, let's just say I was told by someone, do not mention Tom Cruise's daughter in any public thing that I do. Because Tom Cruise is worth 600 million and they want to get money out of him, right? So we can't use Tom Cruise's daughter. Actually, if you try to search her name on the student directory, even like the one that faculty can get to, she doesn't show up. But she's definitely a student, but she's not taking databases. So I don't know her. Okay. So I think, all right, since I started off with the video of Denzel Washington, let's just go with Denzel because he's been in a lot of movies over the years. So this is Denzel Washington in, I think, The Color of Blood in 1981, right? And we'll see how Denzel ages over these years. So I will say, as I said in the beginning, the acceleration of the advancements and developments in AI has also been found in AI for databases or database tuning. So what I'll call the past era is not that long ago. So it's from the very beginning, from 1975 to about 2020. And at a high level, all these tools are look basically the same. And then when LLMs show up, then when things get interesting. All right, so in the past era, or pretty much in all these database tuning agents or tuners, the high level idea is the same. You have some database system that you want to optimize. And so you're going to provide some basic information about what the application is trying to do with this database system, what the workload looks like, what the queries look like, what transactions look like. Then you have some objective function, the thing you want to optimize in your database, like P99, cost, storage rights, things like that. And then sometimes you also provide the environment, like I have this amount of CPU, this amount of RAM, and so forth. And then you're going to feed this information to some kind of tuning agent, who's then going to crunch on it, produce a recommendation of a new configuration that you can apply to the database system that's going to try to optimize your objective function. And then in some cases, at least in the newer tools, you actually get a feedback that you can then send back to the tuning agent and say, you told me to do this, and when I did it, I got this benefit, or I saw this change or this effect. And then in theory, the tuning agent can then refine its decisions and repeat the process to generate a better configuration. Right? So even the modern LLM systems that we'll talk about in a second, they basically look like the same way, that you need some kind of feedback mechanism to say, was that a good choice or not? So there's, as I said, there's a lot of work in this space. People are doing this, trying to solve this problem for a long time. So I'm not going to go through the details of all these different algorithms. Let's just say, this is something that people have been trying to do since the 1970s. Actually, the first paper here for physical design, the partitioner paper in 1976, that was written by my advisor's advisor, and he's dead, right? So this is something people have been trying to do for a long time. But you'll notice that there isn't a lot of choices or a lot of examples for query options and lifecycle management. So for query options, there hasn't been a lot of work in this space until very recently, just because people just assumed the query optimizer would get better, and it's something like Postgres, it's not. So now you need these additional tools to try to make things, try to improve query plans. And you also notice that for lifecycle management, there isn't anything. And we'll see as we go along why this is the case. But pretty much all the tuning tools that exist today, no one can do the sort of look at the broad spectrum, the total lifetime of a database system and make good decisions for it. The best you get are like simple calculators on the cloud vendors to say, oh, you have, your database is this big and you have these number of queries per second. You need to instantize it to this big, right? It's pretty basic heuristics. There's nothing really there watching and learning what your database is trying to do in conjunction with other databases and try to make decisions for you along the way. So we'll come back to this at the end, but most of the algorithms we'll talk about at the beginning, no one's going to do this. All right, so if you want to see how much benefit you can get when you tune these different parts of the database system, right, indexes, knobs, or queries, let's look at a very common benchmark called the joint order benchmark, and we're going to run this on Postgres, and we're going to see what happens how much faster the database can get when you tune these different parts. So the first thing we have here, the stock number, that's like if you download Postgres, do like apt-get install or use the Docker container or whatever, like this is what the package maintainer provides you for the basic configuration of the data system. Right? And it's very conservative. It assumes you have like, 120 megabytes of RAM, right? It's not tuned at all, but they assume somebody else will come along and set this up correctly. So if you tune the knobs using a very common tool called pgtune, which I'm sure a lot of you have applied, you actually can get a reasonable benefit. You can get about 30% improvement, right? pgtune is not doing any machine learning, not anything sophisticated. It literally is like if then else statements. If you have this amount of CPU, then you tell you to set these parameters. If you have this amount of RAM, you set these parameters, right? But even that gets you 30%, so that's pretty good. If you tune indexes for this workload, you can get even more benefit. And again, this is not cumulative, so this is just tuning knobs and just tuning indexes separately. We're not actually tuning both at the same time yet. So if you use Microsoft's latest algorithm to pick indexes, you can get about 48% improvement. There's another open source tool for Postgres called Dexter. If you're familiar with that, that's pretty brain dead. It doesn't do a very good job. The Microsoft one is probably the best one you could use right now. And then if you tune the queries, so this is Postgres, so we have to use PG plan hint to be able to send the hints, you can get about 36% improvement, right? So clearly, we're getting some benefit here from tuning, but again, as I said, we're only tuning these things one at a time. So there's been a bunch of work looking at now how to use sequential tuning, and it's pretty basic. You basically going to run each of these tuners one after another, and you end up with a final configuration after running them in sequential order, right? So you start your database picking with tuning knobs, and then you move on to picking tuning indexes, and then finish all with tuning queries, right? So what's going to be challenging about this is that the order in which you apply these tuning agents is actually going to matter a lot in terms of the actual benefit or improvement you're going to get in your configuration. And it varies per workload, per application. So sometimes you want to tune indexes first, sometimes you want to tune knobs first, and you basically have to try all possible combinations to figure out where to get the best benefit. So if we go back to our benchmark we had before, I'm going to show the best case and the worst case of the different combinations you can have for tuning these things. Right? We ran permutations of all possible combinations, but I'm only showing 2 of them for the sake of space. So if you tune queries first, followed by knobs, followed by indexes, you can get a 67% improvement. But if you tune knobs, followed by indexes, followed by queries, you get an 80% improvement, right? And again, this is for this one workload, the queries index of knobs index queries is the right order, but in other workloads, we find different ones that actually matter. And depending on what tuning algorithm you're using, you may actually want to do one versus the other. So the problem with this is that this is pretty brain dead, meaning like it's just running these tools one after another, and you're never going back and revisiting things. And so that means that you can't tune your knobs, then tune your indexes, and then go back and try to tune the knobs again, right? And it's sort of it's artificially doing this. We obviously can run things again. We'll get that in a second. But the basic way people are tuning these things now, this is how people do it. This is how humans do it. And so the problem is that because you can't go back and revisit tuning decisions you made in the past, you end up having this issue where you may actually not find the true global optimum for your database system. Right? And it's basically the prisoner's dilemma problem, right? So again, we go back to say one query in the joint order benchmark in Postgres, and say I'm just going to tune the queries, and then I'm just going to tune the knobs, right? So if I want to tune the queries, I'm going to have 2 choices, right? I could choose hint 0 or hint 1, and I can calculate what the benefit I'm going to get from each of these by actually just running the queries and see what happens. And so in this case here, hitting 0 gets the biggest improvement in performance, reducing the P99 latency. So I'm gonna choose that, or not the P99, the total runtime. So I'm gonna throw away the other choice and choose the other one. So then now if in sequential order, now I run my, my index tuner, right? I have two choices, index 0 or index 1. I'm gonna end up choosing, in this case here, index 0, because again, I'm seeing the best choice based on what I chose from my query tuning in the first step. But in this simple example, the true global optimum is down here in the corner, but I'm never gonna reach that if I'm only looking at these one at a time and never going back and revisiting. Right? It seems kind of obvious that you might maybe go visit it, but again, this is not what people in general are doing. So that's pretty much the last 45 years of database tuning using automated tools. I mean, obviously the algorithms change over time, the sophistication of the methods change over time, but that's pretty much it, right? So now let's get to the present era of the last 4 years, from 2000 to 2004. And Denzel Washington has aged a lot. I forget what movie this is from, but I think it came out 2018. I haven't watched any of these movies, so, because I thought I was gonna use Tom Cruise and I forgot I can't use Tom Cruise, so it's Denzel. All right, so it's obvious what we wanna do here, right? If we can't do sequential, if we have to do sequential tuning, let's go back and revisit things. And so I'll call this sort of multi-round sequential tuning. And again, the basic idea is that we're going to invoke one of these agents one at a time, but we can then decide to go back and re-execute them again to revisit decisions we've made in the past to hopefully get us to that bottom corner where we reach the global optimum, right? And so there's obviously a bunch of different ways to schedule the invocation of these agents. As I showed, the order can actually matter. So the agent can decide, here's the expected benefit I get, and choose one agent versus the other at each step along the way. And so you typically have this coordination framework that basically says, all right, I know what I'm trying to achieve for my database system. Here's all the different tuning agents that I can choose from. And maybe I'll run through them all sequentially in the beginning. And then if I need to, I can go back and revisit them. Speaking of P99, that's pretty bad. Okay. It's coming. There it goes. Right. And then so I run all these different agents. I can go back and revisit. So there's a paper that came out in 2023 from Alibaba for this project called Unitune, and it's basically a coordination framework that can figure out what's the expected benefit I get from these different agents. And every sort of tuning round, it goes back and says, okay, this is the one I actually want to apply. They use machine learning algorithms to tune the knobs, machine learning algorithms to tune the indexes, but their query tuning is actually just running calcite to do and using their rewrite rules. So they're not doing any kind of machine learning to pick the knobs. We'll see some why that matters later on. But like they basically have a way to decide which of these different agents I want to run at a time. As a side comment, I would say like Alibaba puts out a lot of papers in automated database tuning. It used to be Microsoft was at the forefront, and I actually think Alibaba is. But I just don't know what they're actually running in production, because they're cranking out 20 papers a year. I don't know what they're actually doing. And some of the open source stuff is a little dicey. It doesn't work. Or the paper says one thing, the code says something else. But this one legit, we were actually able to run this, and it does work. Just not that great. All right, so let's go back now. But it's research. It doesn't work, it doesn't work. All right. All right, so now if we go back to, again, the same benchmark we had before, again, we had the single tuners, then we had the sequential tuning, and now we're gonna run Unitune to do the multi-round tuning. For this one, we actually don't get that huge of an improvement. We don't see the huge benefit that we would expect, and doesn't actually even beat the knobs indexes queries example. So we're only getting a 67% improvement in performance. And I bring up calcite because the way they're tuning the query options is using calcite. So it's basically using your rules and heuristics to decide how to rewrite the query. Whereas like the query tuning here is using a reinforcement learning algorithm to actually learn what the right knobs and hints should be. Okay, so the problem with this sort of multi-round tuning is that at the end of the day, it's still invoking each of these agents one at a time. That means that it can't sort of reason about all the possible choices you could have to tune your database system at any one given time. And any decisions or anything that one agent learns during its process of trying to compute what the correct configuration to be, it doesn't pass that along to the next agent. Like each agent basically is its own little island, and they can't reuse the memory of anything they're computing from one invocation to the next. So what we really want is a single agent, not this multi-round thing, not the sequential thing, a single agent that can reason about all possible tuning options we would have in our database system. And then that way we can actually account for any implicit dependencies you may have from different decisions you may make all together at the same time. So by dependencies, I mean things like I may have my index tuner pick certain indexes, but then I don't want my knob tuner to turn off index scans, right? Because then I'm not getting any of that benefit, right? That's sort of a straw man or a simple example, but that's the basic idea of what we're trying to avoid here. If we can think about everything and look at everything all at once. And you start to see, wow, this is going to lead us up to using LLMs. So a simple way to do this would be, if I could just throw everything in a giant pot, pick your favorite optimization algorithm, right? Whether it's Bayesian optimization, it's some kind of deep net thing, and hope you spit out something that's actually useful and makes things better, right? But as I said, just picking what indexes you need is NP hard. If you have to throw all the different options you can have in there, then the combinatorial space or the solution space is massive. We're talking about trillions of different choices, right? So you're not gonna have a good time trying to figure out a good configuration because it's never gonna have, you're not gonna have compute time to figure this out. So the first problem of this, of course, and the number of choices you have is super high. The dimensionality is high. So you can't, it's just too expensive to run these things because you have to test out your configurations on the database system. You have to run queries to see actually whether it makes things better or not. So that's going to be super, super slow. So it's not like playing Go where you can just like make the choice and immediately know whether that was a good decision or not, or play the game out. You actually have to run the queries in the database system, and that's going to take time. The other challenge in this with this problem is that the number of actually good configurations is much less than the number of bad configurations, right? We can do basic things to make sure we don't pick like allocate negative amount of memory for the database system, but there's still enough settings where you know it's going to be useless, but you can't figure that out till you actually run the queries. So we need a way to figure out what configurations actually are going to matter, what choices are going to be good for us, and avoid looking at ones that are going to be wasted time. So the thing that we're going to do to exploit this is that we're going to make the identifier recognize that in the case of database tuning, a lot of the choices we can have are actually very similar to each other. And therefore, if we can learn something about one choice, we can then apply that and infer the benefit or the problems with other choices. All right, so let's looking at some really simple examples. So in the case of tuning knobs, if I set my buffer pool to 32 gigabytes, that's going to be about the same as setting to 33 gigabytes. So maybe if I've already looked at 32 gigs, maybe I don't need to look at 33. And obviously there's a performance cliff. If I go above some number, I could fall over and run out of memory, but we can ignore that for now, right? But in general, this is true. Indexes work the same way as well. If I have an index on column A, well, that's going to about perform the same as an index on column AB. So therefore, if I've tried column A, or index on AB, maybe I don't need to try the index on A. And lastly, for query options, same thing. If I set a parameter that says how much hash memory I should use for joins for one query, 1.0 is going to be basically the same as 1.1. So the basic idea here is that if we can recognize what these similarities are in our algorithm, our tuning agent, we don't have to look at all the trillions of possible choices I have. I can start throwing away things where I may be seeing things that are similar enough, and I know not to consider them again. So there's two ways to say things are similar. One is to say that if the data system is going to perform the same, and the other is going to be if they sort of look the same based on our domain knowledge of databases. So we developed a new algorithm called Proto-X, and we call this a holistic tuning agent, where we're going to look at all possible choices that you can have for tuning a database all at once and not have to run individual agents. And we're going to use an actor-critic reinforcement learning model where we can try things out and then learn whether those are good choices or not. So we call it Proto-X just because, when you submit academic papers to this one conference, it has to be anonymous, right? So you instead of saying like, oh, we're running Databricks, you would say we're running System X or Database X, right? So we're like, all right, we'll call it Proto-X to make it anonymous. But then when the paper got accepted, we just forgot to go change it. So somebody's like, they thought it was like a gang thing I was doing, like a hip hop thing. It really is that stupid. We just forgot to change it. So it's called Proto-X, right? And so this is going to look a lot like almost an LLM, where we're going to take a configuration we have, map it in some kind of high dimensional space with an encoder, get an embedding, and then we're going to have a way to figure out what around us in that high dimensional space looks very similar, and we can choose whether we want to look at those different configurations or not. So the basic idea of the way it works is that, oh yeah, sorry. I don't have a preview here, so I'm watching over there as I go along. So this paper was published last year in DLDB, and I'm excited or proud to announce that this has the most number of characters in a paper title that we have in DLDB the last 20 years. So if you look at the ranking, as it comes up, sorry, we have 161 characters, and the next one is 155. It wasn't the plan of making that many number of characters, but when we found it out, we're pretty happy, and we're trying to get higher going forward. At this point in my career, it's the little things that make me happy. All right, so how's this all work? So we have our configuration, and then we're going to pass it into a configuration that's going to have all the things we talked about before: query knobs, physical design, and system knobs, like all the choices you could have that we talked about before. And then we're going to pass this into a encoder that we have to train that can take this configuration, generate an embedding that then maps into a high dimensional space for this particular configuration as it loads. There you go. And then we'll just do this again for all the possible configurations that we have, and they're all going to map to different locations in high dimensional space. And then now we have to have a decoder that does the inverse, that takes some coordinate in this high dimensional space and spit out reverse it back to the original configuration. We'll have some kind of similarity signal we can calculate aside, yes, these things are being similar based on some proximity, like Euclidean distance or other things. So then we train a decoder that can take out these configurations and then from the coordinates in the space, spit out new configurations. We have to do some extra checks to make sure, like, if it tries to set a buffer pool size at -5 or some negative number, we can throw those things away, say they're invalid. All right, so then now we have our database system we want to tune. And the way this all works with this high dimensional space that we've generated, we take the current configuration that we have, as it comes along, and we'll pass this through an actor, basically the agent component that's going to figure out, like, apply the change and see what actually happens. And then it's going to use that same encoder to go back to the latent space, figure out where it exists in there, then use the similarity signal to determine what nearby is actually relevant, so we can map that back to the original decoder. And then we do a neighborhood search based on whether we want to exploit our history or explore new things. Using, again, that similarity signal, we say, here's all the configurations that are nearby, and it can rank them based on the proximity and expected benefit from the current configuration, and it can decide, do I want to try new ones that are not close to the one I'm currently at now, or do I want to try to hone in and try to look at things that are nearby me? And then there's a critic that takes this ranking, goes ahead and applies the change to the database system, and then we get feedback to determine whether this was a good choice or not, right? And again, repeat this process over and again until you run out of time, or you tell it that it's converged enough and it plateaus and the performance gains, right? Depending on the complexity of the workload, depending on the number of choices you have in your configuration, this can take minutes or even hours. Okay. So I briefly want to talk about the two different ends of similarity. The one is, again, based on performance. Like, if I think that if I've seen this configuration has the same benefit of other configurations that look very similar, then I'll say that they're grouped close together in the high dimensional space. Of course, the problem is going to be, how do you estimate that what the expected performance is going to be? You could run the queries every single time for every single choices you have, but that's very expensive to do. You could rely on the query optimizer and their cost model estimates about the cardinality, selectivity of predicates to try to do estimates, but that's usually wrong, especially in Postgres. We've tried doing approximate query execution, so instead of running the full query, like in Postgres, you can pass a table sample flag to your from clause. So actually instead of running a full query, it just samples the table and runs those queries. The problem with that is that the query plan changes. So now you don't have a correct mapping to what the query that you ran versus the query you ran on the sample versus the query you run in production. So that's a problem. There's a bunch of line of work that we've done and others have done on building machine learning models that, again, sit external to the database system to predict the expected behavior or runtime of queries. And we use something like that to speed this process up. But it turns out the better way to do it is actually apply domain knowledge about what we know about databases and these different choices we could have to say that these things are similar. So one basic thing could be like, if I'm trying to tune the buffer pool size, right? Instead of looking at every single discrete value I could have within a range, like in Postgres or any data system, you can set like the exact number of bytes you want to allocate for memory for the buffer pool. Well, maybe you don't want to look at all these different choices. So you think of like the number line of different choices I could have in my buffer pool. Instead of looking at every single step along the way, I could just say, well, anything from 1 gig to 2 gigs, that's choice number 1. Anything from 2 gigs to 3 gigs, that's choice number 2, and so forth. So now, instead of looking at, again, potentially infinite number of choices you could have, or 0 to the 2 to the 32 minus 1 for the size of your buffer pool, you just have maybe 10, 20 choices. And that reduces, again, the complexity of the search space. For indexes, as I sort of already mentioned before, indexes with common prefixes are going to be classified as similar because we know that the data system is going to be able to use certain indexes if you have the right prefixes in other cases, you would not be able to. So an index on A is equivalent to index on AB, but an index on AB is not equivalent to the index on B. Right? Again, now I know if I try index on AB, I haven't seen what the index on B does, and depending on my algorithm, what the model is trying to do, I may want to explore and try index on B. One of the cool things that we can do that nobody else can do, because again, we're mapping things in this high-dimensional space, it's actually really easy for us to add additional things we can tune, because we don't need a whole different tuning algorithm, and it doesn't add additional complexity to the like the number of discrete choices we have. We actually can start doing additional optimizations or apply additional flags on our indexes that nobody else can, like include clauses. So include clauses, like when you create an index, you can say create an index on table foo on column A, include column B. And what happens is the data system will put the value of B in the leaf pages. It's not part of the key, but it's in the leaf pages. And so that now when I have a query that says like select B from table where A equals 1, 2, 3, if I have the index with the include column, then I can basically do what's called a covering query, where I only have to look at the index to get the answer to the query. I don't have to go look at the original table, right? I don't have to follow the pointer. So that makes things run a lot faster. We did a scrape on GitHub of looking at open source Postgres schema definitions, and we never see this, right? Because humans don't know how to, probably don't know the feature exists, and then people don't know how to set it correctly, right? But actually, in some cases, it can make a big difference. If you're crazy, you put all the columns as the include column, and then you basically have an index organized table. I don't recommend that, but we did see that once. All right, so if we go back to our benchmark we were looking at before, if I want to look at what Proto-X can do, now I'm getting down to almost bare metal speed here in Postgres, which is surprising. And we're getting 88% improvement in performance. Right? Again, because we're looking at everything rather than all at once, rather than one single choice at a time. This is about the best we've gotten. We've tried running almost an exhaustive search, and we're not able to get below this. Actually, that's not true. When we bring LLM, we get a little bit better, but not significantly more. All right, so why are we doing so much better? I think I've already said a lot of this before, and people are probably itching to get to LLMs. So we can tune everything. And it's actually really cool because we don't have to write a whole new algorithm anytime we add a new feature. Like my student added the include columns in like an hour because it's just throwing another feature in the high dimensional space. And then the search algorithm is actually still the same. So we can tune everything you can tune in Postgres, except for table partitions, because that's a destructive thing, right? If you create a table partition on an existing table, you have to drop the existing table, create the partitions, and then rewrite all the queries. It's very expensive to do, and it's not easy to roll that back. So it's the only thing we don't tune in Postgres. All right, we'll do questions at the end, but if you have any questions as we go along, just shout them out. Okay, so Proto-X is great, right? As I said, we published this last year. I think this is the right way to do database tuning, a model like this. But at the end of the day, it's a local only model, meaning, and it's trained locally based on the single database instance, and it's very much customized to the database and the application. And that means that if someone comes along and makes major changes to the application, like they drop a table, add a bunch more columns to an existing table, add a bunch of new features that cause new queries to get executed, then you actually have to retrain the entire model. Now you can cheat a little bit and put like extra spaces in your input vector as placeholders for tables that don't exist yet, but it's not great. But like if you make major changes, you got to throw it all away and start over. And it's very hard to then transfer that knowledge about tuning one database and apply it to another. So what we really want to be able to do is use the collective intelligence of the internet, because people have been tuning databases for a long time, and be able to leverage that information in our tuning agent, and ideally not have to tune from scratch. So this is where you get into LLMs, right? As we get back to Denzel Washington. So this is Denzel Washington in Gladiator 2, which came out in 2024. So the frontier of this really is like the last year and a half. And again, there's a lot of activity in this space, and it's pretty exciting. And again, it's all based on LLMs. So there's a bunch of work being used for LLMs for database tuning. This is just a quick sample of some of the ones that have come out in the, like I said, in the last 2 or 3 years. I'm going to focus mostly on the knob, the knob tuning stuff that we talked about before. I'll talk a little bit about query rewriting, and I'll talk about this upgrade advisor prototype we built, which we haven't published yet because it did not work, and you'll see why. There's the Supabase has their own AI system, but it seems pretty trivial. Sugu can tell me more about this. He's here. There's Tembo. They were a Postgres startup, and now they switched to AI system. A bunch of these performance monitoring ones, they're pretty rudimentary. It's basically relying on, as far as I can tell, like ChatGPT to tell you what's going on with your database, but it's not very prescriptive and it's not very definitive. So I want to focus on the other problems. So for knob tuning, the basic idea is or in physical design tuning, the basic idea is pretty much as you would expect. Like an LLM has been trained on a bunch of information that's out on the internet about people tuning databases, documentation from the manuals, posts on Stack Overflow, posts on the Postgres mailing list, right? So there's a bunch of information out there, people saying like, hey, I have this problem. How do I make my databases run faster? And the LLM can kind of crunch that and spit things out. So the way that has to work is that you have to provide some basic information about what your database looks like, what the workload looks like. And the challenge of that in the early days of using LLMs was that the context, the number of input tokens was quite limited. So you couldn't really say a lot about what your database is trying to do. But this has gotten much better in the last 6 months. So people have been pushing more things into the input prompt and getting more out of the system. The other challenge with using LLMs is that they want to spit out natural text. You can try to ask it to spit out SQL or even JSON of what the configuration should be, but it doesn't always work. And because we find that it hallucinates more when you ask it for structured output, as in JSON, versus freeform text. So now you need another model to parse the text and figure out what the actual SQL commands are. But that's a minor thing. The other thing you got to worry about too is whether you want to prompt the LLM for tuning the entire workload, in which case you need to summarize what that workload looks like, or do you want to prompt on a per query basis? And we actually found if you prompt on a per query basis, it does much better. But the problem is going to be from one query to the next, the LLM may tell you conflicting things. It may tell you to drop this index for this query, but keep this index for this other query. So you have to have some extra steps to resolve those issues. So the basic idea is something like this. So I have my prompt. I'm asking it to recommend configuration parameters for Postgres to optimize the system's performance. I give some information about what my resources look like. I have 8 CPU cores, 32 gigs of RAM. And then I pass this into my LLM. I can fine tune it if I want. And then I'm going to get out some output that sort of looks like this, right? And then I have additional step to make sure that this is actually valid commands. There's no negative numbers. It's gotten much better at not hallucinating tables that don't exist. Early days, it would always spit out tables from TPCH or very common database workloads. But it's gotten much better in the last year or so. So the thing that we care about this down here, this additional context, right? What do we want to put in here to provide information to the LLM about what our database is actually trying to do so that these recommendations are targeted for our workload and for our application. So there's a paper that came out last month or 2 months ago at Sigmod called Lambda Tune. This is work done by Emmanuel Trammell at Cornell. He, in my opinion, is at sort of the forefront of all this LLM for database tuning and LLMs for databases. Like one of his first papers, DB-BERT, was training an LLM based on documentation of Postgres and the mailing list, and it showed some early promising results from that. What's really fascinating about this work is that they're going to try to do workload tuning. So they want to, in that additional context, they want to summarize what the workload looks like. And they're going to try to tell the LM, here's what my joins are. Make sure you pick the right indexes for these joins. And so if you can't fit all the joins in your workload in the prompt, they run an integer linear program to decide what's the optimal number of joins to then spit out to the LLM based on the expected result. So it's sort of marrying classic ILP or interlinear programming optimization problem with something like an LLM. Like it's sort of optimizing the prompt that you give to the LLM. So we go back to our graph again, and now we throw in Lambda Tune here. Maybe it's too late now. I was gonna say, let's take a guess whether it does better or not. It doesn't, right? And the reason is because it's not doing query tuning here. Right, so in Lambda Tune, it can only tune the indexes and tune the knobs. It can't tune the queries. If you then go run this query tuning algorithm as well, it'll knock off maybe like another 60 seconds on the query, so maybe like 190 seconds, but still not even close to what Proto-X can do. But it's doing better than the Alibaba tool, but still not as good as our sequential tuner from before. All right, so Proto-X can still beat LLMs, at least for now. That's good. But what's the one thing I haven't told you about or talked about at all during this process? What's that? Fucking. I would be a happy man if I can get through a talk with somebody not asking about blockchains. I don't get blockchain emails anymore. That has been good. I feel good about that. Okay. Anybody else? What's that? Upgrades? No, not yet. Lifecycle? No, not yet. What's that? No, schema. Runtime. How long does this all take? Well, Proto-X, we let it run for 12 hours, and you get that. The LLM can spit this out in 14 minutes. Right? Because and the reason why it's 14 minutes because they're trying out multiple times, multiple prompts, and then try to pick out which one's the best one at the end. And then resolve any conflicts that they have trying to pick things out. Right? Now, is this a fair comparison? Sort of, but not entirely, right? Because you think about Proto-X is training from scratch and has to learn everything, like a newborn baby about the world, about your database. The LLM somehow magically has a bunch of shit posts on Stack Overflow about how to tune databases, and it can just reuse that. It doesn't always get it, it's not always great. But I would say, like, you know what? That's actually not bad. To get, most of the benefit in 14 minutes versus 12 hours, that's actually pretty good. That's a fair trade-off I think a lot of people would make. Again, certainly at scale, right? If you have thousands of databases, you don't want to run 12 hours per database, right? Is this being recorded? Yeah, all right, sorry. Let's just say there's a well-known company that sells databases, and they may own a Hawaiian island. That's too obvious. Let's just say one of the things they can do is that if it's on-prem, not in the cloud, but on-prem, and it's your hardware, they train these models in the background all the time because they're burning your cycles, not theirs. So for them, maybe that's not a big deal. But for most people, this is problematic because you're paying for this, right? All right, so the other challenge we have to face is, yeah, the LLM can do this in 14 minutes, but are these kind of benefits you're getting or the improvements you're going to get, is it transferable beyond the workloads we're looking at here? So the join order benchmark came from the Germans. It's basically the IMDb database with a bunch of different queries doing OLAP stuff, right? It's a well-known benchmark that's been around for about 10 years now. And so there's a bunch of posts on the internet, a bunch of papers on the internet to tell you how to make these queries run faster. So is the LLM really learning something about your workload and making good decisions, or is it just hard-coded and make that query run faster? So how do you get around that? Well, the Cornell paper says if you obfuscate the query, then they didn't see any difference in performance, the benefit you would get from the LLM using the anonymized query, the obfuscated query versus the original query. The problem is these LLMs are really, really good. So even if you obfuscate it, it can figure out what the hell you're sending it, right? So if you take this query here, I think this is query 16A, and then if I change all the table names to be random, random things, and then instead of having hard-coded constants, like where country equals Germany, if I replace that with a UDF as a placeholder, so it doesn't actually know what the constant is, the LLMs can still figure this out, right? So if you give it to Gemini, you give it to ChatGPT, you give it to Claude, they come out pretty quickly and say, hey, I know what this is. This is from the Jordan benchmark. Let's see if this video plays here. So this is actually running on Claude. So again, this is taking the obfuscated query, and it can figure out exactly, can't definitively identify what the benchmark is, but it seems like it's coming from the Jordan benchmark. And then it spits out a bunch of recommendations of what indexes to pick, right? Using all the obfuscated names, but it matches pretty much with what you would get with the original query. So the LLM in this scenario for this workload is actually hard-coded technically for that synthetic benchmark. So how well this is going to work beyond the standard benchmarks, it remains to be seen. And the recommendations are pretty good. I think when I ran this query, you got about 20% difference. So we'll come back to that, how to tune LLM or tuning the data system with LLMs in a second. But I want to talk about query rewriting and then this other lifecycle management thing we haven't touched yet. So as I said, query writing, the basic idea is that you take your SQL query and the query optimizer sucks. So you're going to run it through some rewrite phase that kind of contorts it into a form that the query optimizer is going to be better able to deal with. And then you run that query. So you can do things like convert nested queries into joins, move expensive operators to like in and out of CTEs and so forth, right? Remove surplus operations. It does a reasonable job, but in our experiments, and I don't have results to show here, it'll spit out, the LLMs will spit out SQL that is actually correct, like it's syntactically correct. It'll compile and actually run, but in many cases, it's actually semantically different than what your original query was. There was a tool, I think it's still around, called EverSQL. I'm not trying to knock them, but they're the biggest one. Like for that thing, we would give it queries and would come back with things that are correct and was all proud of itself. Like, look how much better we made it for you. But you definitely run it, you definitely got different results. Like it would move order by clauses in ways that it shouldn't be, right? Because they were blindly taking whatever the LM spit out and giving it back to you and letting you try to figure out whether it was actually correct or not. Which again, if you've seen some really big SQL queries, it's just impossible. So there's a bunch of work done by actually Alvin Chung, who's now at Berkeley, but is at UW, and actually trying to verify that two queries are equivalent. He had a project called COSET and a new one called QED Solver. The idea is you can take two arbitrary SQL queries and it'll tell you whether they're actually semantically the same or throw its hands up and say, I can't tell. So this is fantastic. We had this would solve this problem, but these solvers actually can't handle all possible queries. Like I don't think the latest one even handles CTEs or an all kind of correlated subqueries. So we played around with maybe taking the rewritten query, running it in a sandbox on some sample data and like doing like fuzz testing. And that seems to work, but again, you can't prove that still that these things are going to be, semantically the same. So I say this is the one area I think could be a lot of work to be done, but you still need extra boundaries or constraints to make sure that your LLM is not going to cause problems. All right, the last one I'm going to talk about is version upgrades. So this project was inspired by a blog article that the Neon guys wrote that came out last year. And it's actually something we saw at AutoTune, my previous startup as well, where people don't upgrade their database system, the software version. And rightfully so, because it's like, you don't know what's going to happen when you upgrade. And so people run with whatever version of Postgres or whatever version of MySQL that they had when they first created the application. And only when the database vendor, like Amazon, tells them they have to upgrade, or it's been end of life or sunsetted, that they don't go ahead and then try to upgrade, right? So even though Postgres puts out a new version every year, people are still running on the old versions because they just don't know what's going to happen when they upgrade. So we've been trying to solve this problem, and it's really interesting because it's much harder than than picking what index you want or picking your knobs. Because if you get that wrong, it's pretty trivial to roll things back. If you upgrade, your version of Postgres, and now 1% of the queries that you really care about are running much slower, you're screwed. You basically have to dump the database and load it all back in. It's very time consuming. So we tried building a recommendation advisor where we could say, this is what my queries look like. Tell me whether if I upgrade to Postgres, upgrade my Postgres version, am I going to have problems? And so we trained or fine-tuned a Llama 3.2 using the mailing list or the Postgres developer mailing list, because that's where people post all their performance issues after they upgrade. It doesn't show up on Stack Overflow because they want to go directly to the developers and say, hey, I upgraded to Postgres 18 or 16, and I'm seeing these issues. So my student fine-tuned the model and built a little RAG application for this as well. It works sort of, but the problem is the LLM basically became an asshole because it's trained on all these mailing list posts of people complaining, right? So I show a little demo of this. So this is just running the demo here. So we give it a prompt. Basically, this is the mailing. You're trying to be you're a database, sorry, a Postgres expert. We want you to solve this person's problem. And it comes back saying it's a lot of read the manual. Why are you doing this? This is not a good question, right? Stuff like this. And it's also very interesting because there's some very well-known database contributors or Postgres contributors like Bruce Magim, Tom Lane, and it'll attribute quotes to those people that are clearly asshole quotes. You should one was you're brain dead. You should not be using Postgres. Signed Tom Lane. I'm that's not good. So we abandoned this project. Let's just say we think we can solve this by not using, or LLMs can help a little bit, but fine tuning on certain things doesn't make sense. We're actually looking at using LoRa's to take you train a LoRa per version of Postgres. So in that way I can intermix them and say, I'm running on Postgres 13. What happens if I upgrade to 14, 15, 16? And you can do the same thing actually for hardware upgrades as well. So that gets into the sort of lifecycle stuff that I was talking about before. All right, so that's a sort of crash course on what how LLMs being used to tune databases in the last, like I said, year and a half. Let's look at what's going to happen in the future. So this is Denzel Washington in a movie that I forget what it's called, but it came out 2 months ago. So he's looking grizzled there. So the LLM stuff I think is super fascinating because essentially what you're doing is being able to learning from prior knowledge. But the challenge is that the LLMs are sucking a bunch of information in, again, from mailing list posts, from Stack Overflow, that's unstructured and doesn't have the full picture of what your database is actually trying to do, right? It's sort of giving you generic good advice, but not really targeted exactly for what your database wants. And so therefore, you're not going to ever achieve that full benefit we can get in a specialized algorithm like Proto-X, right? And so I think the future is going to be some kind of combination of using LLMs, but as a reasoning agent to guide us for pushing us towards what we think is the right thing to focus on for the given predicament or given situation that our database system currently has. And we also want to be able to leverage LLMs to essentially maybe bootstrap these algorithms so that we don't have to, again, train from scratch every single time and can transfer knowledge from tuning one database and apply it to another database, whether that's in the same organization, like the same company, or across my entire fleet, or across multiple companies. So we have a prototype of a new paper that we just submitted. It's not published yet. And now we're up to 200 characters, or over 200 characters. So I'm pretty excited about that. And so what we're doing here is we're going to use LLMs to what I call boost our tuning agents to basically push them towards a good initial configuration so that when the specialized algorithm starts running, it's not tuning from scratch like I was doing before. And what this allows us going to do is, again, it'll let us do knowledge transfer from one database to the other. The LLM can handle all that for us. So again, for every new database that comes along, we don't have to start over and do that 12-hour tuning. We can sort of pick up where we left off and learn from some of the mistakes we made from one database to the other. So if we go now to our simplified version of the benchmark we've been showing, so this is with Unitune, Proto-X, and the Lambda tune. So these are the original numbers that I showed before. But instead of invoking these tuning agents first by themselves, if we run the boosting agent that runs off an LLM first, then run the tuning algorithm, it actually helps all these algorithms, right? So we can get down Proto-X quite significantly. In the case of Lambda tune here, we're getting a huge benefit from LLM-based tuning because our booster can actually tune knobs for queries and query plan hints in a way that the original algorithm could not. So this is running on Llama 3.2, the 85 billion parameter model, which, I mean, I think this week there's been 3 major models come out from Anthropic and OpenAI, and Quan's got the other one. There's a lot of new models coming out. We're still running on the one from last year, and it does reasonably well. So I think with a better model, we think this can be even bigger improvement. And again, I don't have to change my tuning agent. I just put this boosting thing in front of it, and I get all the benefit of LLM tuning, but then can hand things over to the specialized tuner as well. And the agent only runs for less than an hour, and I get that huge benefit. All right, this is not my work, but this is something I think is really interesting. And I was at Google yesterday, and I was hoping that I asked them to make it open source. They said no. But they have a paper that came out this year about proposing what they call a foundation model, where think of like the same way that you have a giant LLM that can handle any possible text or anything you throw at it, and a bunch of other multimodal tasks. But there's a bunch of things in the LLM that we don't care about. I don't care about Charles Dickens. I don't care about reciting things from Wikipedia in the LLM, but it's in there. But what if you can build a large model that was just for databases, right? Whether or not you have one for MySQL and Postgres and all these separate systems, or just one giant one, it's unclear. But the idea would be that you'd have a single model for all possible applications and scenarios and hardware, and using a mixture experts approach, you can then have it tune different things or handle different scenarios all in one. And you don't have to retrain this thing from scratch. So this would take a lot of money to do and a lot of time. Like just for their prototype, they had to run 100,000 queries from their internal workloads. I don't have access to 100,000 queries. I don't have cycles of 100,000 queries. So this is something that really has to come from a major company like Google. And whether or not they open source it, they're never going to open source it. But I can at least dream. So I think this is the right way to go forward, rather than training these specialized models, but this doesn't exist yet. So one thing we can do to try to cut down on the cost of training these things is, at least in our examples, everything that I showed here, is actually not the training time. It's actually the training data collection to build the models, because you have to run real queries to understand the behavior of the system and then feed that into your model, right? So it's not like in like robotics or self-driving cars where they build simulators and run the simulator and get that as your training data. You actually have to run the query, because the amount of effort it would take to build a simulator for something like Postgres or MySQL or even DuckDB is just as much amount of work as actually building the database system. So no one's going to build a simulator. So we had the idea of like, what if you could use the data system as a simulator as itself, and then have a sort of accelerated mode where you don't actually run the full query, but you still get all the training data you need, right? Because training these models, you don't care about the result of the query. If I run select star, I don't care what the output is. I just care about what the system did when I actually ran the query. So we have a paper came out last year where we have extensions to Postgres that we can switch into like a training mode, so that when it runs the query, if it recognizes that the training data that it's generating is very similar to what it's seen before, then it knows just to stop running. So you can go from training some of these models that collecting training data would take from 2.3 days down to 15 minutes. Okay, so with the exception of the upgrade stuff that I talked about, pretty much none of these are about handling the lifecycle issues we talked about in data systems, right? And so they're also only targeting one database at a time, right? There's one database that's an island by itself. How do I tune it? But in reality, major organizations have a number of databases, and you need to be able to reason it across multiple databases to get the true benefit, the true optimization possibilities that are out there. So there's a bunch of other challenges you want to face. Like everything I've shown before, it's what I call preventative care. Like, hey, I know I want my queries to run faster, they can go. But there's a lot of times where there's an emergency, like I'm thrashing the disk, I'm crashing, I'm running out of memory, and I want actions to help me fix things right now. And none of these models can actually handle that. So this is not entirely public yet, although that's messed up, but whatever. But this is something that we've also been working as well with my students. My previous startup is dead. This is our new startup called So You Don't Have To. And this is the sort of, I want to say it's AutoTune 2.0, but this is the next version of a automated database tuning as a service. And you can rely on LLMs to basically reason about what the system actually is doing right now and decide which of these tuning actions we actually want to apply. Because I said, in the case of Proto-X, it can run for a couple hours and it's going to get amazing benefit for you, but it's going to take a long time. But if my database is on fire right now, I don't want to wait 12 hours to figure out what to do. So maybe I want to run the cheaper tuning algorithms. So we rely on the LLM to figure out those things and understand the relationships between databases, how things move from from staging to production and so forth. And so this is the big thing we're doing next. So the legal name of the company is SYDHT DTC. We tried to incorporate as so you don't have to incorporate it, and then with the drop table companies at the end as a SQL injection attack. Let's just say the IRS, well, you laugh. The IRS did not laugh. The state of Delaware did not laugh. So this is the legal name, but our lawyer advised us we can go as trading as with the full SQL injection there. So I'm hoping this will reduce the amount of spam that I get from people that are just scraping things. So GitHub had no problem with it. Crunchbase had no problem with it. So that's pretty exciting. So there's not much to talk about now, but we have more to share later on. All right, so to finish up, tuning database holistically by looking at all the problems at once, I think is the right way to go. And the proof is in the pudding. We're seeing much better performance benefits you're getting if you can look at things all at once. And if you can reuse the prior experience we have from tuning things in the past to help our guide our decisions going on right now, we can do much better. And that's what LLMs basically are doing. Like it's the past history of people tuning databases just in this sort of chaotic, unstructured form, but it does pretty well. But if you can kind of guide it and make it more structured, you can do even better. And in my opinion, again, the reasoning agents tied together with these specialized algorithms is where you're going to get most of the benefit. All right, so before I go real quickly, I want to talk about two things. One is that we're having another seminar series this semester. This means the future of the database systems. It's on Zoom on Mondays at 4:30. It's open to the public. So if you guys want more databases in your life, please join us. So the theme this semester is going to be on sort of Iceberg and Iceberg-related systems. Although Databricks hasn't cleared legally the Iceberg guys to give a talk, but I put the logo up anyway. And then we actually just got the Mooncake guys agreed to give the talk as well. So they're also going to be giving a talk. So again, that'll start on September 22nd. And you check out the website for more information about that. And the last thing I want to announce is that we have a new program this semester at Carnegie Mellon in our database group. You might have seen this post on Hacker News a few months ago, about this guy named Preston, who is currently in prison in upstate Maine for drug smuggling, right? There was a TechCrunch article, he wrote a blog article about it. He now works, while in prison, he works for Torso, working on the rewrite of SQLite in Rust. So people saw this? If you read the blog article, down there in the middle of it, he talks about how while in prison, he learned databases by watching our course lectures on YouTube. Are you applauding me or him? Because he's in jail for smuggling horse tranquilizers, right? Let's not. All right. No, so he sent me an email back in March, thanking me for this before all this all came out. And it was really touching. He gets out, I think he gets out in November. It's not clear, but he has a job while in prison working on databases, and that's super exciting. We're happy to help make that happen. So we have a new program this semester. I realize everyone is here right now, not in jail, but if you end up in jail and you want to take our course, if you send an email here, we will make all our course materials available to you. We'll send it on a thumb drive. We'll hide it in a cake, whatever you need us to do. We will try to facilitate this. And I want to thank our friends at Convex for sponsoring this. Okay? All right, with that, I'm happy to answer any questions. I'll be here all night. Thank you for coming.